Good morning, everyone. I wanted to talk this morning about the opportunity, energy-saving opportunity of VAV flow reductions. So we'll touch a fair bit on Guideline 36 and how VAVs operate, but also just kind of want to give an overview of the potential opportunity and, well, save energy in just about every building, just the broad application and potential for this, I don't know, pretty common measure, and kind of go through what goes into it, what kind of information you need to capture, and how the calculations are done at a high level without getting into too much of the nitty-gritty. But yeah, if you have questions about any particular slide, feel free to just raise your hand. We can cover it then, but yeah, we'll certainly leave some time for questions at the end. So what is the opportunity? I didn't do this study. This is something published by ASHRAE that was part of the research that went into ultimately the Guideline 36 publication and such. But what you can see is conventional VAV logic. Most of the time, VAVs spend their time kind of in the 30 to 40% of their design airflow. With what is called dual maximum logic, which is what is described and published in Guideline 36, that moves considerably lower, down below 20%. So going from kind of 30 to 40% window to the 10 to 20% window for the peak. There's a lot of energy savings to be had in there, not just fan energy, but cooling or heating energy as well. So this, I think, really does a really good job of capturing and illustrating how much that needle can move, lower, and also kind of sit a whole lot flatter. So yeah, we'll operate still at 30%. There's a small little, minor peak there, but it's a whole lot less than the very pronounced peak that we see in kind of conventional logic that is, rampant in most of the existing buildings that we find. So yeah, I had all this animations. So yeah, reduce fan and cooling energy. And I guess it also has the opportunity to, from an operation standpoint, to extend maintenance intervals for both fans and, filters and belts, because the fan's not running as hard. You're not moving as much air across filters, so it stands to reason that filter intervals and belt intervals would be extended. So should kind of show two relics of VAV control. Is kind of how they operate. So the oldest school one has, as deadband as you're satisfied. As the temperature in the space gets warmer and you need more cooling, you just provide more air to the space. As you get into a heating situation, you need a little bit of heat. All that happens is just open the reheat valve more and more. As you have more call for heat, open that valve more. So the only two airflow inputs or variables that you need are a maximum cooling airflow set point on the kind of top right, and this minimum / heating airflow set point that it operates at the rest of the time. And again, this minimum airflow set point tends to be, from kind of my design days, rule of thumb would just be, whatever 40% of your maximum cooling is. If that was 1,000, this would be 400. Maybe 350, possibly as low as 300, but there wasn't a lot of science or thought that went into it. It was just, that's just the minimum. It's just put 40% in there, and that's the default. You did a lot of calculations to determine the load for what the maximum one should be for heating. Just make sure there's enough BTUs going into the space. Didn't matter if you're supplying 95 degree air or 120 degree air. As long as there's enough heat being supplied into the space, didn't matter really what the airflow was. Reflect on that. That's just really a thoughtless and haphazard kind of approach, but that's how design was done, and I suspect to a large degree still is done. Stepping forward a little bit in time, see that you still have the maximum cooling airflow set point, you still have a minimum airflow, but then when you get into heating mode, whether it's, you have just a modest call for heat, or a full scream for heat, the airflow set point steps up something above the minimum. So that might still be 1,000. This might still be like 300, and then the heating airflow set point might be 400. Not a whole lot more thought goes into this. It's just a slight incremental step up. So 3 airflow set points for all the variety that this would bring about. And like I said, these are not 30 to 40%. Your heating could be potentially maybe as high as 50%, but usually these are still pretty low with that. Oftentimes you may see, if you've poked around in VASs, they're the same. Like oftentimes these are the same value, and so you get into, you look at a screen and you say, oh, it's at maybe 350 CFM. Well, is it in heating mode or is it not? Then you have to, you can't tell at a glance what mode it's in. You have to look then at the reheat valve. Is it operating? Is it open or not? Or what is the discharge air temperature if that's a point in the VAS? So yeah, this is a slight improvement on the last slide, but the dual maximum logic is kind of the state of the art. This is what is described in Guideline 36. So there's a lot more going on here. You have still the cooling maximum airflow in the top right. As you have less and less call for cooling, you'll see you come down to a cooling minimum. So you need to define the minimum cooling airflow. You need to define your actual deadband minimum, and then it'll step back up again as you get into the heating regime, and you'll have a heating minimum, and then you also have a heating maximum. So they call it a dual max. There's a cooling maximum, heating maximum, but there's also 3 different minimum values that need to be defined. In a very simplistic approach, they could all be the same value, but as I mentioned on the last slide, that doesn't tell you at a glance, at least, what mode the box is in. So having some differentiation between those 3 values, the cooling minimum, the actual deadband minimum, and then the heating minimum, you can see, hey, if maybe they're all right around 350, for example. If hopefully there's a little more thought that goes into it, and we'll get into that. But maybe the cooling minimum is 375, the actual minimum is 350, and the heating minimum might be 360. So there's just a little bit of difference in between them, so you can see, oh, okay, just at a glance you can know what, you're close to satisfied or you are satisfied, so the box is satisfied, but which mode is it actually in without needing to display yet another point on the graphics. To implement the dual max logic, the maximum, from one of those earlier versions of logic, what does it take? You still need the maximum cooling airflow. That's going to be unchanged, whether it's the oldest school or old school version. Then you're going to need to define the minimum cooling airflow. You're going to need to define the deadband minimum. You're going to need to define the minimum heating airflow, and then you need to define the maximum heating airflow. I'll admit right off the bat that the heating maximum airflow is still a bit arbitrary. It can be, just rule of thumb, 50 to maybe 70% of the cooling design the cooling design maximum. But the big trick is to make sure, through Guideline 36, make sure that you're delivering the number of BTUs that the space requires or that the box is originally scheduled for, but that you're delivering those BTUs at no higher a supply air temperature than 90 degrees. There's logic in Guideline 30, or in Guideline 36, it describes how you don't want to supply air into a space more than 20 degrees above that space temperature, just because you get thermal stratification. Hot air rises, and if you're only supplying a trickle of that air into the space, then it's not going to mix very well. You're going to end up, sort of with an exacerbated stratification. Does that all make sense? So these green asterisks indicate, and certainly, so then there's this extra point that wasn't on the last slide, and that's a vacant or a standby minimum when nobody's in the space. If the building's occupied, nobody's in the space. You can lower that minimum airflow even lower than what was on that graph. Those were all for an occupied space, but if you can determine that the space is vacant, all the better. So the green asterisk indicates that you should use the ASHRAE standard 62.1, which is the standard for ventilation. They have the multi-zone VAV calculator tool that I have a couple screenshots of, and it's designed to help show how, or to help you calculate airflow, minimum airflows to zones based on however many people are in there and whether it's in heating or cooling. So again, as I mentioned on the last slide, you probably between these three minimums want to keep these values. They can be similar. You probably want to have some distinction between them, maybe 5 CFM apart, to be able to tell just at a quick glance. So how do you calculate these values for dual max control? You use the multi-zone VAV ventilation calculator for all those ones that had the green asterisk. That requires knowledge or takeoffs of the floor areas of the zones, which is a tedious thing to do, admittedly. But that's a required input. So if the client has zone areas known, fantastic. They have scaled, clean, scalable PDFs of their drawings of their building. Okay, we can do the legwork and do those takeoffs. You also need to understand what are the space types. So a conference room is different than an open office right outside, which is different than an atrium or a lobby, just in office buildings. Classrooms are different, auditoriums are different, so they have different populations and zone densities. So when we say zone densities, we'll see on the next slide. But if there's a placard maybe outside a room that says maximum occupancy, however many people, snap a picture of that. It's really useful. That's more definitive than saying, oh, it's a 1,000 square foot room and the default occupancy is 35 people per 1,000 square feet, so there's gonna be 35 people in there. Well, if the placard outside says 45, then that's gonna make a difference in what the ventilation requirements are gonna be for the space, which dictates how low you can actually set those minimum values. The other component or the input is going to be how low can the VAV controller actually measure. That's going to be a limitation, is how sensitive is the VAV box itself and how low can it control to. And VAV boxes, they don't actually measure airflow, they measure velocity. And so this 0.004 inches water column, that's a default. Most boxes, modern boxes, can go down to 0.001. So this is a quite conservative estimate. Depending on the vintage of the box, if the box is 20 years old, maybe you only want to go to 0.008. But in any case, even old boxes are at least this sensitive. It's just a matter of how conservative we want to be. But VAV boxes, they measure air speed, and then you multiply it by the cross-sectional area of the duct, and that gives you the airflow. Yes.
Is there a general rule of thumb around percentage airflow in a VAV, what that minimum should be so that you don't run into the situation where you lose the ability to measure that velocity? Can you simplify it to a base percentage, or does it have to be represented in?
I have a chart on an upcoming slide that I haven't actually done that calculation, because it would be a function of, you would use a box that, maybe has a maximum of 500 CFM, but that box might only have a cooling, depending on zone size and zone load, might only have a maximum cooling load of 200 CFM. And in another instance in the same building, it may have a maximum cooling airflow of 450 CFM. So to say that it's always going to be 15% or 20% of that isn't really a good, it would be a function of the max box flow, which is
Got it.
getting into manufacturer data rather than zone demand.
Okay.
There we go. So then there's this other variable that's like inherent in the controller. It's called the amplification factor, usually indicated by F. If that's not given, we can calculate it. And yeah, so these last two items here are used to calculate the minimum controllable box flow, which is going to be also a big limitation or big consideration in all this. So getting into ASHRAE 62 ventilation, there's kind of two components here. There's the area component, the people component. The area component is measured CFM per square foot, and the three values that are usually given in Guideline 62 are 0.06, 0.12, and 0.18. Yes, they're just multiples of 0.06. Depending on the space type, like if it's a fitness workout area, it's probably going to have, a higher CFM per square foot. And there's also the people component, which is CFM per person, and that's usually 5, 10, or 15 CFM per person. And that is, again, based on the kind of activity that people are doing. If you're sedentary, if it's an auditorium versus a conference room, it's probably going to be 5 CFM per person because people are just sitting down. If it's a manufacturing area where people are on their feet and moving around, it might be 10, might be 15. Although the density, the maximum occupancy, how many people in that space is going to be highly variable. So this is a look at the chart that's in the back of, or it's in standard 62.1. So you can see, CFM per person for just different types of spaces, and this is only a small snippet. There's a whole lot more space types, but yes, the area rate for storage rooms is 0.12, even while the people component is still 5 CFM per person. Excuse me. But yeah, this kind of trumped in terms of the people. Rather than just saying, 50 CFM per 1,000 square feet, that's great. Well, 87 is a far more justifiable, defensible kind of number, if you can snap a quick picture of that. Here's showing some of the equations that go into this is the amplification factor, and the input that we need to capture from a VAV box, which is usually on the sticker on the side, is that box's CFM at 1 inch of water column pressure drop. So we'll show you on the next slide what that can look like. Most modern boxes can control down to 0.004, and if you want to be really conservative, you could use 0.008 instead of 0.004. And down here we're just saying that the volume is the minimum velocity, lowercase vm, is minimum velocity times the area, gives you the volumetric airflow, CFM per square, minimum CFM.
James, how does that pressure at the box relate to differential pressure that you're measuring at the air handling unit? There's obviously like parameters that you want to stay within. You can't go down to 0 for a differential pressure reset.
Right.
But how does that minimum on a differential pressure reset relate to a box, like individual box minimum?
Largely they're unrelated. I would say that the box minimum is going to provide a floor. Ultimately, it's going to provide a floor for what your like air handler minimum would be, and it's not exactly 1-to-1. But you can't have an air handler minimum, like you said, of 0. You probably can't have an air handler minimum of like 0.2 either, depending on where that's measured in the ductwork. But yeah, this is at the boxes with the damper wide open. And once your damper starts closing, that's still the minimum sensitivity of the sensor. But yeah, that's they're correlated, but they're not directly related, I guess would probably be the short answer. So here's a picture from the side of a VAV box, and we're trying to see, well, what is the gain factor. Anybody remember what the gain factor was a function of in terms of what
minimum values?
Yeah, so we're trying to calculate the minimum airflow, minimum controllable airflow for the box. But do you remember what that was a function of?
Area over CFM squared, right? Or area
Yeah.
times that factor.
So yeah, the CFM at
At
1 inch pressure drop.
Yeah.
So thankfully this box has, has all the way up to 1 inch pressure drop, and it has the CFMs listed. Like, that makes it super easy. You don't have to guess. Unfortunately, this isn't always the case. Sometimes, same manufacturer, you get this. So, yeah, okay. Well, I guess that's an inch. And where these lines crossing is logarithmic, so it's not linear. You take some guesses.
Drawn by hand.
Yeah, you take some guesses. So ultimately, this is just a snippet of the spreadsheet that we used to calculate these. It was where the actual CFMs, actually it's from this one we said like, oh, this crosses, it looks like it's maybe just a shade above 900, so we'll call it 910, for example. Not an exact science when you're doing this without the values, but so we said, okay, the 8-inch box is at 910, minimum velocity pressure sensitivity of 0.004 inches. You kind of plug these numbers through. Good. It's good that the minimum controllable velocity is the same for all of these. And then based on the box size, 4 inches converted to what's the cross-sectional area there would give 15.5 CFM. And then in terms of the values we want to control to, you want to round up from there just to be a little safe. So we said 20, and these, again, how much safety factor you want to put in here for 96.84. You could maybe say 100 or 105. You said 110 in this instance. So yeah, maybe you could say 250 for this bottom one. I said 275, which compared to the actual controllable flow for the box, it's doing like a couple thousand CFM. So getting down to whether it's 250 or 275, it's a significant reduction from what probably the minimum airflow for that box is currently set to. I'm running long, so I want to keep cognizant of time. So this is just a quick snapshot showing this actually 62 multi-zone calculator. It'll highlight the what's called the critical zone, so the one that is like closest to being at meeting 100% outside air. And yeah, what do we want to show here is the this is from a hotel like conference space, conference building that I was working at toward the end of last year. They had this lecture hall with 100 fixed seats, like 10 rows, 10 seats across. So okay, zone population is 100, maybe 101 if there's a presenter. So 100 people is the zone population, and that means a minimum in cooling mode of 822 CFM based on the square footage of the room times the area, CFM per square foot, and then the 100 people times 500 times 5 CFM per person. So that gives 822 CFM in cooling mode. In heating mode, what's different here is that this ventilation efficiency or ventilation effectiveness, because, let's go back to the cooling, it's 1 for cooling. In heating mode, it drops to 0.8 because in this particular space, the hot air, the supply air is coming from the ceiling and it is returned at the ceiling, so guideline 62.1 or standard 62.1, says that only 80% of that fresh supply air is getting into what they call the breathing zone, which is like below 6 feet in the space. What's curious is it doesn't matter whether it's a 10-foot ceiling or a 40-foot ceiling, it's still 0.8. But in any case, that dictates the effectiveness. So for the same space, but now you're supplying maybe 80, 85 degree air into the space. Still 100 people, but now you need, over 1,000 CFM is your minimum controllable, your minimum ventilation requirement for that space, assuming that it's fully populated. Now, when you go to, this is the vacant standby scenario, zone population goes to 0, and hey, what do you know? We only have to ventilate 200 CFM, which is actually less than, so the minimum, this 200 is not a function of the ventilation, that's just as low as that box can go. That's an 8-inch box, or sorry, a 14-inch box. It can only go down to 200 CFM. You only need to ventilate like 130 CFM into the space for that condition, but we can't control to 130, we can only control to 200. So yeah, that's that. And ultimately the output of all of this analysis, this is kind of what we gave the client is, hey, here are those, all these different scenarios, and here's what you should be controlling to for each zone. And yes, there's not a box 4-4. They just skipped it. So yeah, this is ultimately the output. It's just, hey, controls contractor, as you're reprogramming logic, plug these values in instead of what was there. So obviously a little more thoughtful. There's some analysis and engineering went into it. But what might jump out at you is the ventilation CFM for this, like, hey, 155. All right, that minimum is 170. So there's a little bit of a factor. Just rounding up slightly. 155. We're controlling to 155. These other two zones, though, the 37 and the 63. Well, we're only going down to 75. So that what that tells you is that the boxes for this, or what the size of the box is, what's limiting these minimum values. So if they were doing a renovation, maybe downsizing those boxes is an opportunity. So you could drive this one down to, I don't know, 40. And restrooms, admittedly, restrooms aren't a great example because their airflow is more dictated by exhaust requirements, but the point remains. So yeah, just going through these, this is, what were the airflows of this system when we found them. So the baseline value, it was, for this first one, heating airflow was 500, and so these are the different scenarios that guideline 36 has, but it was using one of the old school methods. So, well, if it's heating, whether it's minimum or maximum, it was still using its 500 CFM value. So what you'll see for this VAV box number 1 is that, well, we're going up in airflow, yes, from a minimum of 500, what it used to be, to 1200. The difference, we're ventilating properly and they weren't ventilating properly. Same thing for the baseline heating flow. It was 1,022, so rounded this up to 1,030. Yeah, well, they weren't ventilating adequately. We're taking, again, they weren't ventilating adequately even in their minimum situation. And in the, so yeah, this VAV41 shows that, yeah, they weren't ventilating adequately. Pick any of these others though and see, well, it looks like they weren't ventilating adequately for most of these in the heating scenario. But when you go to the baseline minimum, and again, this 280, this is kind of the 70% of the max cooling airflow for that box. So it is actually a slight energy penalty, but the amount of time that the box spends there is minimal. It's very, very infrequently at full heating. So the amount of savings that you see in all these other modes more than offsets that by like tenfold. So yeah, kind of on average, you can see that heating mode is 71% of design flow on average. The baseline, the minimum heating is only 38% of design flow. The big thing to take away from here is that 14% of design flow is the vacant or standby mode. So that's really where the opportunity is to drive boxes So do they have an occupancy sensor? Do they have CO2 for demand control ventilation? Being able to determine if a space is vacant, and therefore being able to drop out that minimum, the people component of ventilation allows you to operate in this regime a whole lot more. And that, going back to the kind of the first graphic, allows the peak of that chart to move, lower and lower, further to the left. Yeah, it's just comparing the differences in. Whoop, didn't mean to do that. No, it was touch sensitive. But yeah, so the minimums between just deadband and the baseline, like there's a huge reduction here. You go from 825 down to 200. A lot of these are similar, and that tells you that the limit is more dictated by the size of the box. But going from 170 down to 110, 155 down to 75, 190 down to 75, like those aren't modest reductions, percentage-wise. Those could be pretty significant. So yeah, and that'll tell you. Well, the one that has the biggest reduction is this lecture hall VAV41. If you only had the budget to install one occupancy sensor, that would be where you want to do it, because the difference between these boxes is the largest there. There could be other inputs like how often is that space used versus maybe other spaces that are used a lot more or less frequently. So don't let that be your only guide, but that can inform a whole lot. Right there. And lastly, this is just a screenshot from that BAS, and you can see they only had cooling max airflow and